From the mobile studios of Way Happy, this is Mr. Meyer, and we are at Ida Homes Park here in beautiful Livermore. And we are going to talk about 1-3, the 12 basic functions. So what do you have to know? You are responsible for knowing 12 functions. That's right, 12 parent functions. I will do the piecewise one in class, but let's get started. What do you need to know? All that vocab from 1.2 is going to come in now. So the first one we're going to talk about is a linear function, probably your most common, so it's a good one to start with. It is y equals x, the one you know the best, right? A nice linear function. I would plot some points of it, so like 0, 0's on there, 1, 1, 2, 2. How about -1, -1, and -2, 2? That's what our graph looks like. And if you have the graph, you can pretty much answer every question you want, like, what is the domain of our function? So if you look at that, our domain is going to be all real numbers. So you can write all real numbers, or you can say from -infinity to infinity, not inclusive. The range, same exact thing. You could say all real numbers, right? Or going from the bottom to the top, -infinity to infinity. Either one looks good. The symmetry of this, if you notice, this graph looks like it's reflected over the origin. So therefore, this is what we would call an odd function. Boundedness, there it is not bounded, so none. Asymptotes, there are no asymptotes. Discontinuity don't exist because this thing is continuous through the entire graph. Never had to lift my pencil when drawing it. Notice it is increasing the entire time, so I would just call this graph increasing, or you might say it's increasing over its domain, which means the entire time this is present, we're increasing. Extrema, since it's increasing the whole time, it can't have any extrema. There's no maxes or mins or anything like that. And last but not least, the end behavior. So look at the end behavior. The limit as x goes to infinity, that's the right side. The function y equals x goes to, I should just say x. Let me change that. The function x heads to infinity. And the limit of the left side as x goes to -infinity, the function heads to -infinity. And there you have a complete analysis of the linear function. What about graph number 2? We are going to talk about graph 2, which is the squaring function, also known as a parabola for most of you. Also known as the quadratic. So its equation is y equals x squared. Now I like to plot some points there too, like 0, 0, 1, 1, and 2, 4, -1, 1, and -2, +4. And there is a beautiful graph that you can now answer everything of, like domain, all real numbers, or -infinity to infinity. The range, look at that, it's everything bigger than 0, but 0 is included. So let's go from 0 to infinity for the range. Symmetry, this is an even function. See the x-axis symmetry. So therefore, I'm sorry, y-axis symmetry. So therefore it is even. It is bounded. Yes, it is. It is bounded below. Right? Bounded below. There are no points below one of those points. So it is bounded below. There are no asymptotes. Discontinuities, none. It is continuous on its entire life. Notice that this graph is decreasing. Remember, we go left to right. It is decreasing from -infinity to 0, and then it's increasing from 0 to infinity. Extrema, it has an absolute minimum at the point 0, 0. And the end behavior, the limit as x goes to infinity, the right side, the function x squared goes to infinity. And the limit as x goes to -infinity, that's the left side, the function goes to infinity. And just a little heads up, what people will then sometimes do is, since the limits are the same, they will write this as the limit as x goes to plus or minus infinity, the function goes to that same thing, infinity. So they'll condense that down to one thing just so it looks a little prettier. And that is 2 of your 12. Number 3, let's talk about the cubic function, or what I like to call the John Travolta. The John Travolta, y equals x cubed. Right? 3 points, you could do 0, 0, 1, 1, -1, -1. No, it shoots off like this. and it shoots off like this. If you've ever seen Saturday Night Live, you know why I call it the John Travolta function. That's what he looks like. The domain is all real numbers, or negative infinity to infinity. The range, all real numbers, negative infinity to infinity. Symmetry, this is an odd function because it looks like it's rotated over the origin. Boundedness, it has none. Asymptotes, none. Discontinuities, none. It is increasing over its entire domain. So this is an increasing function. You could say over the entire domain, or just call it increasing. And extrema, it has none then. However, some people will talk about this point as a point of inflection, that one in the middle where it looks like it's going to be a max on one side and a min on the other. They'll mention a point of inflection. And the end behavior, as x goes to infinity, the right side, the function goes to infinity. And the limit as x goes to negative infinity, the right side goes, or the left side goes to negative infinity. And there is your cubic function. Now, let's jump into the inverse linear, also called the reciprocal. Now, this is the first one that, you have to kind of pull back on some memory, I think. Y equals 1 over x. That's where the reciprocal comes from, right? Now, it has a vertical asymptote because the denominator cannot be 0. It has a vertical asymptote right there at 0. It has a horizontal asymptote right here at 0. First one was x equals 0, that one's y equals 0. Be a little careful there. And when you say those, well, I'll wait till I get to asymptotes. The 2 points I like to label, I'll label the point 1, 1 and the point negative 1, negative 1. And then I'll draw the graph in here. It looks like this. It's a hyperbola. Kind of like a regular hyperbola, and there's the graph of it. So what is its domain? Its domain is all x's except for 0. So how do I write that? Well, negative infinity to 0, not including, and 0 to infinity. And the range will be the exact same thing, starting at the bottom, negative infinity to 0, and 0 to infinity all the way at the top. Does it have symmetry? Yes, it's an odd function. Looks like it's a reflection over the origin. It's bounded. No, it's not. Asymptotes, yes. Now, this is where you got to be careful. You got to tell me that there's a vertical asymptote when x equals 0, and there's a horizontal asymptote when y equals 0. Now, you can't just say there's a horizontal asymptote at 0 because I don't know what that means. You got to go ahead and tell me horizontal y equals 0. Discontinuities, this is an interesting one. It does have what we call non-removable discontinuity. It has what I would call infinite discontinuity. This graph is neat too. Notice if you start on the left, it's decreasing the entire time. Then you jump up here and it's decreasing. So it's actually decreasing over its entire domain. So we would say it's decreasing over its domain. Now all that means is I don't have to worry about saying it, something weird's happening at 0. I can just say if you look at the domain, which is already defined to the left there, it's decreasing over that entire time. Therefore, there's no extrema. And then here's some interesting end behavior. The limit as x goes to infinity, the right side, for some reason I'm doing that first all the time, 1 over x, the right side is headed towards 0. And the limit of the left side, 1 over x, is also headed towards 0. And there are your first 4 functions of our assignment. Let me ask you a question, and I'll get right back. All right, nice work. Now let's keep moving. Parent function number 5 is the square root function, or what I call a shooting star, because the graph to me looks like a shooting star. First thing you might want to notice is that I will label 3 points. 0, 0 will be there. 1, 1 will be there. And let's go, 4, 2 would be another nice one to have. And as you can see, the graph is a shooting star looking like that. Domain. Notice the domain goes from 0 to infinity. Notice the range also going from 0 to infinity. The symmetry, there's none. Bounded below, notice that there's nothing below that point, so we will call it bounded below. Asymptotes, there are none. Discontinuities, there are none from when the graph starts, so no discontinuities over its domain. It is increasing over its entire domain. So I will say increasing over the domain. Extrema, there's none. And the end behavior, this is where it finally gets a little weird. What is first I'll do the right side like I've been doing. So the limit as x goes to infinity. Notice that the right side, the square root of x, that's headed to infinity. But what's the left end behavior? Remember, end behavior means at the far left, as you go way over here on the graph, where is the graph at? Well, that's what's kind of weird. We call that it does not exist, or you can't do it, or if you remember Mean Girls, they said, right, the limit does not exist. That's what's going on right there. There is no limit on the far left end. This is saying go to the far left end, and there is nothing there. It doesn't exist, so therefore I will say it doesn't. And that's your shooting star graph. Now, what about exponential functions? A little heads up, the book uses y equals e to the x, which is great. E is 2.7, but we better do all of them, right? So remember that if the base, the thing getting the exponent, if it's bigger than 1, that's called a growth graph. If it's smaller than 1 or between 0 and 1, it's called a decay graph. Just which way it opens. So here's my growth graph. I will label 2 points. Now it's a little tricky here because one point will always be 0, 1, but the other point will always be whatever. It depends on what that b value is. Say it's 5, then I would have to, if x was 1, I would have to go up 5. So I don't want to put any tick marks here because it's b. So that will always be a point on your graph, 1b, right? And you have an asymptote, horizontal asymptote cruising along right here at y equals 0, and then your graph looks a little something like this. It starts at this asymptote and then shoots through those points. And so if we go ahead and take that, our domain then looks like all reals. Our range is everybody bigger than 0 but not including 0, so be careful. Our symmetry, we do not have any symmetry. We are bounded below, and you can see the vocab now is really kicking in from last section. There's an asymptote. Heck yeah, there's a horizontal asymptote at y equals 0. Discontinuities, there is none. It is increasing all the time. Therefore, it doesn't have any extrema. And its end behavior, the limit as x goes to infinity of b to the x, if it's a growth graph, that's where it's going to be kind of tricky. If b is greater than 1, then that limit will be to infinity, and the limit as x goes to negative infinity of b to the x will be 0. But this is for growth. Now a little heads up, a decay graph, all it's going to do is flip this graph around so it looks like that, like the red one. We'll notice the end behavior on the left side is now going to infinity and the right side is now going to 0. And we will do more with that in the different sections, but just to get now a little heads up, when we're going to be talking about transformations too. All right, what about a log function? Now again, I might as well do log of any base. Your book will just do the log of base ln. It'll just do natural log, so log base e. But let's do any of them. The 2 points that in a vertical asymptote, it will have a vertical asymptote right here at 0. So at x equals 0. It will have the one magic point right here at 1, 0. And you will always have another point that will be whatever the heck your base is, right? So whatever b is, comma 1. That will always be there. And so this is what a log graph looks like. And so now I can go ahead and do all the parts that I need. The domain is going to be everything from 0 to infinity. The range is going to be all real numbers. Symmetry is going to be none. Bounded is going to be none. Asymptote is going to be a vertical asymptote when x equals 0. Discontinuities are none. It's increasing. And it's got no extrema then. And then the end behavior, the limit as x goes to infinity, the right side is going to be infinity. I guess I'll call it log of x. That's going to be infinity. And the limit as x goes to negative infinity, there's that crazy one again. What is it doing on the other side? It does not exist, right? So therefore, there is your log function in function 7. How about function 8? What about absolute value graphs? Again, absolute value, kind of a fun one. You go plot some points, and notice it's only here in the upper regions. What does it look like? It's y equals absolute value of x. There's your graph. The domain is all reals. The range is 0 to infinity, but it does include 0. The symmetry, that's an even function because it has y-axis symmetry. The boundedness is below, that is bounded below. There's no asymptotes. There is no discontinuities. Notice it is decreasing from negative infinity to 0, and it is increasing from 0 to infinity. There is an absolute min at 0, 0. And the end behavior, I'm going to use the shorthand. The limit as x goes to plus or minus infinity of the absolute value of x is infinity. And that is number 8. Now let's take a little break and we'll finish up the last couple when we get back. All right, now we get into the last couple that may or may not be new to you. The first one is the greatest integer function, and it looks like this, kind of an absolute value bracket. Or sometimes I've seen it written like this, right? It's called the kind of like a rounding down function. You want to round like birthdays. You know, when you're 16 and a half and somebody asks you, how old are you? And you're like, oh, I'm 16. You kind of rounded it down. When you were, 23 and 3/4, you tell people you're 23. And that's what this function represents, a rounding down of it. Now, it's got some interesting points, like it's actually range of points. 1, 1, 2, 2, 3, 3, -1 would all be on there. But because of the nature of rounding down, if your x's, let's say the x is between 0 and 1, say it's 0.8. Well, 0.8, you'd have to round it down to the nearest integer, so you would round it down to 0. And in fact, everything between 0 and 1 would be rounded down to this range, except for then 1 would jump up. Everything between 1 and 2 would be rounded down to 1. And so this graph has this unique, what looks like a bunch of steps. And a lot of people will call this a step graph. So because you're always rounding down the values that you have, it creates this beautiful step. Now let's talk about the fun parts of it. Now that we see the graph and we're like, all right, the domain would be all reals. The range, pretty difficult, right? Because do you see the range is just all integers. So it would be all integers. Some people use the letter Z for that. The symmetry, this has no symmetry. The boundedness, it has none. Asymptotes, it has none. Discontinuities are kind of interesting, right? Notice that it has a jump on every integer. So I would say that discontinuity is a jump or a non-removable, a jump at every integer. It is not decreasing or increasing, but interesting thing is it is a constant. See those little constant steps? It's constant between integers. So kind of a nice thing to say is it's constant between integers. No extrema, and the end behavior is a little crazy, right? The limit as x goes to infinity, the function also heads to infinity. The limit as x goes to negative infinity, the function heads to negative infinity. And that is your crazy one, number 1, right? Now, what about the logistics equation? The logistics equation is kind of like a growth, and it's an interesting one. It is y equals some number, so we'll say 1, over 1 plus e to the negative x. Now, this one is got 2 asymptotes. One asymptote is always at 0, so that's kind of nice. The other asymptote is wherever the numerator is. So the other horizontal asymptote, whatever the numerator, for us it's 1 this time. And then the 1 point you will have to figure out, there will always be 0, let's say 0, half on this one. And what the graph looks like is it starts off at this asymptote, then it takes off like a growth graph, but then it hits this asymptote and mellows out, and that's called a logistics graph. We get into them a lot in chapter 6, so don't freak out too much if you're like, whoa, I don't know what it is. And the way you could find a point is you could just plug in, 0 comma whatever and see what you get. That's how I got the point 0 1/2. I plugged in a 0 for x, and I had 1 over 1 plus 1, right? Anything to the 0 power is 1. And so that's how I got the half. The domain is all real. The range for us, this time it would be between 0 and 1, but not including those because it never touches them. The symmetry is none. The boundedness is bounded. So that's kind of cool. We haven't had a bounded one. Remember, that means bounded above and bounded below. The asymptotes, they're there. We have a horizontal asymptotes, and we have them at y equals 0, and in this case y equals 1, the numerator. It is continuous, so there's no discontinuities. It is increasing, believe it or not, the entire time. There is no extrema. And last but not least, the end behavior, a little interesting. The limit as x goes to infinity, notice that, I'm just going to call it the function, goes to 1. And the limit as x goes to negative infinity, the function heads to 0. Now, I just did that because I didn't want to write the whole long equation. And that is your logistics. And then we got 2 more, right? We have a sine and a cosine graph, and we will spend also some time on those, so I'm not going to go too crazy on you. But all you'll have to know for these is that sine has its little pattern starting at the origin, and it looks like this, and then it just repeats. Its domain is all reals. The range is between -1 and 1. Excuse me, it includes those values though. This actually has odd symmetry. It is bounded. It has no asymptotes, no discontinuities. It is increasing sometimes and decreasing sometimes, so we'd have to find a fancy way to talk about that. And we would also talk about the extrema. We could talk about maxes and mins coming every, depending on how much trig you've done, they are showing up every once in a while. And the end behavior does not exist because it constantly bounces between a high point and then a low point. So I don't know where it's going to be at the end. So therefore the end behavior does not exist. And so again, they're going to do these ones a lot more, but just to give you a little info on them, there it is. The cosine graph, which is also that, does this exact same kind of pattern. They're not Jaws teeth, so don't make them pointy. Try to curve them a little bit. But you can see the domain is all reals. The range is from from -1 to 1. And the symmetry is even, and it is bounded, and that's about all you need to know. And then finally, we can talk about piecewise in class. So there are 12 of them. Good job. Stay happy. And now we're going to do some evaluation of ones that are maybe shifted. Have a great day, and I'll see you tomorrow.